Welcome to this ICRR seminar. I'd like to start by acknowledging the Behavioural people who are the traditional owners of the land on which we are meeting, and to pay my respects to Aboriginal and Torres Strait Islanders, past, present and emerging. So this morning we've got a talk by Dr. Alice Mason. Alice did her PhD in experimental psychology at the University of Bristol in the UK. She then did a postdoc at UWA in Perth, then another postdoc in Warwick, back in the UK, and is now a lecturer at the University of Bath in the Department of Psychology and the Institute for Sustainability and Climate Change. So also a kind of interdisciplinary type of institution like the ICRR. I've known Alice for, I don't know how many years now.
Maybe like 8, no.
10?
10, yeah.
A long time. She's a lovely person. I've really enjoyed this project that we've been working on together that you're going to hear about a little bit today. She's a regular visitor over here, which is terrific, and I'm hoping that this will lead to future collaborations and work. And we're interested in everyone's ideas and insights and ways in which we could move this project forward. Yeah. Okay. All right. So over to Alice. Thanks very much.
So I just thought I'd start by saying a little bit about the Institute for Sustainability and Climate Change at Bath. So it's it's a merged institute. So they wanted to set up an institute for climate change, kind of focusing on behavioural science, but there was already an Institute for Sustainability, which was like predominantly people in chemistry. You can't have the same members of staff as part of 2 institutes. And so now we have this really interesting institute that's only just opened, I think, like a couple of months ago, that is basically half chemists and half psychologists. So it's going to be really interesting to see how that, they've got loads of big plans on how to bring everyone together and do interdisciplinary stuff. But yeah, so I gave this talk actually at their summer showcase last year to a room full of chemists, following a talk by a guy who had given a really detailed mapping out of how recycling plants work. So I don't know how this audience will find it, but we'll see. Okay, so I always start by asking people to have a think. I don't want to hear your answers, but just have a think in your head. If you were asked, what do you think the average temperature increase, so global mean surface temperature, will be by 2100? So if you would just ask that question, what would you come up with? And I'm going to come back to that in a minute. Now, the experiments and data I'm going to present today, I know that we did some experiments on the general public and also on climate scientists. So I'm aware that some people in the room might have taken part in that, and I will be showing you your data later. So when we ask people to think about different climate futures, so I'm talking about the general public here, we often present the possible futures in terms of these scenarios. And this is an example from a media article on sea level rises that gives some projections along with these different scenarios. And you can see that the scenarios, they often choose the kind of an optimistic one. So this is the one at the top. The regional rivalries, kind of slightly the business as usual, and then a fossil fuel development, so a worst case scenario. So this is how we're kind of typically communicating this information to the general public. And most people or lots of people in this audience will have more familiarity with those scenarios themselves and where they come from. So these are modelling scenarios used to explore future emissions, impacts, and adaptation and mitigation strategies. And there's a way to move that little 2 out of the way.
I don't know why that's there.
Well, hopefully there won't be too. Oh, there is some stuff down there. Oh well.
You know what?
Try?
Yeah. It's just the monitor.
Yeah. So these scenarios make a range of different socioeconomic assumptions, and so the SSP1 that will make quite positive socio-economic assumptions, and therefore that will be your kind of best case scenario. And then at the other extreme, you'll have a worst case scenario. So we summarize these for the general public, typically in terms of this idea of a current trajectory, a best case, and a worst case. And when these are communicated to people, they are communicated with these estimates that usually have an upper bound and a lower bound. So it could be for a global mean surface temperature or a sea level rise. So why are we asking the general public to think about things in this way? So these are kind of these modelling scenarios that are filtered into how we're asking people to think about climate futures. Well, understanding this perception of risk communicated by these projections has become important across a variety of sectors. So in the financial sector, both in the UK and in Australia, there's been this recent legislation that requires businesses to report climate resilience against a range of future scenarios. And the interesting issue here is that the onus is placed on the business and the individual to select their scenarios themselves to report against. And so what this does is it requires that decision maker to understand the uncertainty about the likelihood of various different scenarios, and also the uncertainty about the likelihood of the values in the range communicated by the scenario. So that upper and lower bound expressed in the scenario. And so then what we have is we have people grappling with these two different types of uncertainty. So the first uncertainty is this deep, irreducible uncertainty about which scenario, the current, the best, the worst, or any other number of possible scenarios that could eventuate. Then we also have this uncertainty about the likelihood of the values within the numerical range expressed in that scenario. And both these types of uncertainty, either independently or in combination, are going to have an impact on the types of judgments and decisions people make on the basis of this information. So I've explained that these scenarios are accompanied by these numerical ranges. And I just want to say a bit about numerical ranges and why they're typically communicated to people. So we use them in science communication to communicate uncertainty. And they've kind of taken off in particular because there's been research that suggests when you communicate uncertainty from an expert, people have more trust in that expert versus when you just say, you know, it will be 2 degrees. So you can think about the range as sitting on this scale of uncertainty communication. And this is decreasing precision. So the most precise communication of uncertainty would be to give people the full probability distribution of these values. And then at the other extreme end, you could say there's no uncertainty. And so that range providing a range sits relatively close to providing a full probability distribution. But there's obviously a gap there. So what we're interested in is how do you get from this range to a full probability distribution as the decision maker? So if you were given this range of 2.1 to 3.6 degrees, there are various interpretations you could make to get to the underlying probability distribution. And so somebody who thinks that the values in the middle of that range are most likely would be inferring a normal distribution of those values, whereas somebody who thinks that all the values are equally likely would be inferring a uniform distribution. So you can start to see now how, on the basis of the same information, people could perceive the underlying risk of those ranges to be quite different and therefore make different decisions on the basis of that information. You've also got, if people inferred that values either at the lower end or the upper end were more or less likely, they'd be inferring a skewed distribution there. So that's the kind of the basis for the experiments that we have been running. So we're interested in how people perceive these ranges to be distributed, and also how people perceive the likelihood of these different scenarios to occur and the interaction between those two things. So our first set of experiments were on the general public in the UK. And we've got a sample size of 1,099 people who participated in those. And that's actually, I think it's about 7 experiments that followed a very similar structure and had various small manipulations that we didn't find to have a main effect. So we're just collapsing across those to present the data today.
I'm trying to fix it for you.
And then we also have this sample of UK and Australian climate scientists. I was about to ask everyone who took part to put their hand up, and then I was like, I don't think you're allowed to do that. That would be very unethical. So, and we're really, it's obviously really hard to get that sample. So very pleased that we did, but then obviously 82 people isn't very many to make any inferences from. So I was warning you there that I haven't got a lot to say about that. So across all the experiments, they follow a really similar structure. So we present people with these 3 scenarios. We have a current trajectory, a best case and a worst case. Once they've seen these scenarios, we ask them, which scenario do you think is most likely to happen? And we also ask them for each of the 3 different ones, what they think the different, excuse me, I can't see it, how likely they think the different values are in the range. So that's basically where we're asking to estimate this underlying probability distribution. That's right. So I'll just give you a brief overview of what the scenarios were people saw. So the current trajectory, so for all the scenarios, the description of the scenario was purposefully kept very brief. So it's just like the current trajectory is business as usual. The countries meet the targets and pledges they've agreed to. And then we provide people with the statement that says scientists expect an increase of 2.8 degrees. This could be as low as 2 degrees or as high as 3.6 degrees. So they are given a mean of that range in addition to the lower and the upper bound. We did run versions of the experiment where they're not given a mean, and it didn't impact the overall findings. So then the best case is simply that we exceed these targets and pledges, and the mean is 1.9 degrees. It could be as low as 1.5 or as high as 2.4. And then we have our worst case scenario where we fail to meet all the targets and pledges. And this is an expected increase of 5.6 degrees. It could be as low as 4 or as high as 7.2. So everyone will see all of these scenarios. And for each one, they'll be asked the following question. So this is an example for the worst case scenario. You're then asked, do you think that all the values in the range are equally likely, or do you think some are more likely than others? And it's a multiple choice question that people can respond with the following, one of the following responses. And each of these responses maps onto a distribution shape. So as I explained earlier, if you think they're all equally likely, it's a uniform distribution. We've got a normal distribution. We've got a U-shaped distribution, and then we've got 2 skew-shaped distributions. So the upper values are more likely, or the lower values are more likely. Once you've seen all the scenarios, you're just asked, which scenario do you think is most likely to happen? Now, is there a correct answer? So Ben and I spent a very, very long time trying to work this out, and I don't know, thank you to whoever, wherever in the ICRR came up with this. But well, the first thing to say is that for the purposes of the data that we're presenting today, we're not actually interested in whether there's a correct answer. We're interested in how people's responses differ across the scenarios and according to their predictions about which future we end up in. But I have been told that in the limit, you would expect these predictions to be normally distributed, but obviously the models that they come from aren't necessarily independent, and it will depend on how many models are included. So it's sort of unanswerable, but we kind of say possibly normally distributed. If anyone has more to say on that, we'd be interested to hear. I'm seeing some faces at the back. Okay, so we had what possible outcomes did we?
Sorry, can I ask a question on that? Did you consider expert consensus?
Do you mean on?
Is there a correct answer?
Yeah.
I'm just interested because we're struggling with that as well on another study. I'm just wondering.
So, well, I guess we asked climate scientists these same questions. So I suppose when I show you the data, would that count as expert consensus? Because if all the climate scientists give the same answer, then would we expect that to be the correct answer?
Well, that could be a benchmark against which you could
Yeah.
compare the lay populations assessments.
So I won't give a spoiler for that, but because otherwise we'll have nowhere to go if I give a spoiler. But yeah, it's interesting, but I think the main thing here is to say, well, obviously, in some ways you want people to be correct. If you're the scientist and you're trying to communicate something, you want people to be correct. But given that it's incredibly complicated and there may or may not be expert consensus, what can we learn from the patterns and the ways that people do respond about this maybe gap in the communication and the perception?
I've got a very quick follow-up question. Is there any way to check if these people really understood what you mean by equally likely, skewed to the right, skewed to the left? So
I think in terms of,
because I've got very, very little confidence in people understanding what a probability distribution is.
Yeah, so that's why. So because, and we'll come on to that again later, but one thing you could do is you could ask people, how are these distributed? And they would have to choose between normal, uniform. So I would also have very little faith that people would necessarily get that. I don't think
even my students understand what a probability distribution is, even if I spend weeks telling them this is this stuff.
That's why. So the wording of this question is chosen to not actually mention a probability distribution. We're inferring the distribution. So the purpose of this is just to be in kind of plain English about likelihood of outcomes. And I would hope that people have some ability to answer that. And I mean, I think our results show that they do, right? So when we come on to that, I'd be interested to see if you think that...
I agree on, I hope they have an understanding. Yeah. I'll question if they really have an understanding of what is it, but that's a different discussion.
Well, hopefully if in terms of that sort of simple English, I think they probably do have an understanding. They probably don't have an understanding of not everyone has an understanding of how that maps onto the distribution. And we'll come back to that. So in terms of the possible outcomes, one hypothesis would be that for all of these different scenarios, and irrespective of what you believe is likely to happen, people provide the same answer for everything because it's a range. And this hypothesis comes from work from Dieckmann and colleagues. So they have looked at how people respond to numerical ranges. And some of the numerical ranges they've given people are to do with climate projections, but some of them are just to do with, like, you know, how much corn a farmer has produced. And they ask people, they give them a range and they say which values are more or less likely. And the most common responses that people give are that things are uniformly or normally distributed. So that's one hypothesis. The other hypothesis is that people are influenced by their prior beliefs about climate change. And so they answer the question in line with those. And this is kind of called motivated cognition. So what you think to be happening, your reasoning is affected how you respond to these questions. And so Dieckmann and colleagues ran a study different from ours, because I should have mentioned, all the people in our study have said that they believe in climate change. So these guys ran a study where they looked at people who had more or less climate acceptance. They didn't give them different scenarios, they just gave them a single range. But what they found was that the people who had more climate acceptance were more likely to believe that values were normally distributed than the people who had less climate acceptance. So what this is suggesting is your beliefs, your climate acceptance, influences how you respond to the same types of information. Okay, so I'm going to now give you an overview of our results. So the first interesting thing that we can see, can't see, this might be a problem for the results. Ideas there. And what is, oh, it's to say that the screen is 1 or 2.
Yeah. That's what I'm trying to do. If we can have 2 minutes, probably. Yeah.
Dialogue box actually.
Yeah.
Yeah.
Tim?
Is there a cursor?
We need everyone.
Alright, Tim's gonna just. It should just be.
Yeah. Together, then we can go into sync.
Doesn't
Yeah.
need 5
Yeah,
people.
How many?
Get rid of that. Oh,
It's gone.
Right.
It's gone.
online also.
I've lost the
unseen
entire presentation.
presentation. Yeah.
Oh, the number's gone. The
Yeah.
number's gone. Quick, just put the slideshow back.
Okay.
So it goes back once you present.
From
Yeah,
screen.
like that before.
Did they? What's on?
Yeah.
It's off. Although we need to get back to the Zoom because people can't see the presentation. Open up.
Sorry, Zoomers.
So many reasons to be sorry for those Zoomers.
Screen 2.
There is one more. Oh, it's gone.
Yeah, we've now got it.
All right.
Oh, no, we don't. Tried. Here it is. Yep.
Okay.
All right.
Okay.
There
All
we
right.
go.
No.
Sorry, this is the best
Right,
part.
there we go. Yeah.
Yes.
Okay, so when we asked these 1,099 people which of the scenarios they thought were most likely to happen, this is what we found. So we found that the majority of people, so 61% of these people, thought that we were most likely to end up along the current trajectory. And we call these people the maintainers, so maintaining the status quo. 17% of people thought that we would end up in the best case scenario, and we call these people the optimists. And lastly, 22% thought that we would end up in the worst case scenario, which is the pessimists. And I just personally was very surprised by that, given the numbers in that worst case scenario. So that was an average increase of 5.6, as low as 4 and as high as 7. And we've got 22% of people, the general public, thinking that that's most likely. So what we're then interested in is we split our people to belonging to one of these 3 groups. How does that influence how they responded to those questions about the likelihood of the different ranges? So the first group I'm showing you here are the maintainers. Okay, so that's 61% of people, and they all saw each of the scenarios: the best case, the current, and the worst. And then on the right-hand side, you've got this key for the distribution responses that people could give. So the grey colours are the normal and the uniform, and you'll see that across all scenarios, that's the most common response that people give. And then you've got this brownie colour, which is the U-shaped. You can see a very small proportion of people think that these values are U-shapedly distributed. And lastly, so I'm not really going to speak much about the U-shape because it's a really small proportion, but the 2 skewed distributions I think are really interesting. So the upper skew means that you are endorsing hotter temperatures being more likely. So that's why it's red. And then the lower skew means that you are endorsing the cooler temperatures. So that's blue. And what you'll see is that if we look just at those skews, for the best and the current trajectory, people were more likely to think that the hotter temperatures were most likely. And then for the worst case, this flips and they think that the cooler temperatures are most likely. So we're already seeing evidence that they're not responding consistently across scenarios. The scenario is impacting your response to this distribution question. Now, if we introduce the data from the pessimists, you'll immediately see that there's much more red here. So we do still have about half of people thinking the values are normally or uniformly distributed. But for the skews, the hotter temperatures are consistently endorsed more often than the cooler temperatures. And then finally, we bring in our last 17% of people, the optimists. And again, you'll immediately see that this is very blue. So for the best and the current scenario, still around half are endorsing the uniform and the normal. But when we get to the worst case scenario, half of these participants felt that the cooler temperatures were more likely or were most likely. So it is becoming clear that people's prior beliefs about these different scenarios is having an impact on how they answer the same questions about these numerical ranges. We're not seeing that people are responding consistently across scenarios, and we are seeing some evidence for this idea of motivated cognition. So we were quite interested in how your beliefs, or what might people's general beliefs be about global mean surface temperature increases. So if we look, that little screenshot there on the right is just a reminder of the maintainers' responses. So that's the majority of people. So these are the values that they saw. So in the best case scenario of the skew types, people were endorsing the upper. Same for the current, they were endorsing the upper, so put the values in bold, and for the worst, they're endorsing the lower. So you could argue that there's a kind of inferred range of temperature rises between 2.4 and 4 degrees. So we just kind of wanted to get a feel of whether that was consistent with what people generally thought. So I'm now interested in this room's a bit different from a general public room because it's not the general public, whether people in this audience is that question I asked you at the beginning, was the temperature you had in your head between those two values? Yes. Well, we asked 196 people, again on prolific UK sample online, what they thought. This is just one question, really short experiment. What do you think the average temperature increase will be by 2100? And we did say global mean surface temperature. And these are the results. So what we see was that the median response was 3 degrees. But there was quite a range of possible values, but it was interesting to see that that kind of is about what people might be thinking, that main group of maintainers when they do the experiments.
Did you give them a 0 to 10 range, or could they have put like 100?
They could have put anything, and I think we had like 2 people that put 1,000, and for the purposes of the graph I just cut it off because it was really annoying. I was like, okay, you could, but there wasn't, it was like it was free text, and most people put between 0 and 10, and then yeah, a few people put really wacky things.
Could they put negative numbers?
They could put anything they wanted into the free text box.
Did you recruit only climate believers or believers and deniers?
So this is all believers.
Fear some 0.
The values that are the sort of modal values that you see there, are they, if I type into Google
Yeah.
that question, right? Because I would have no idea if I was asked that question. So I would immediately just say, all right, I'll ask Google and find out.
Do you think, would you have no idea?
I mean, look, I know it's not 1,000 degrees, right? I know it's somewhere between 0 and probably about 5 or something.
Yeah.
But in that range, I wouldn't.
So I guess one thing we could have done is given people, said like, give us a range and give us a best estimate rather than just give us a best estimate, because you could then say, I don't know, somewhere between 0 and 5. We did tell people not to look anything up online. We said just go with your first kind of response to this question.
Right.
And it was done before you got the nice AI summary on Google. So
Okay. The peaks that you've got there, yeah, very, they're at unusual values, like 2.4 and 2.6 or something. It's like, which is not a number that I would pull out of the air unless, so maybe it suggests.
And I think the other thing that if I was doing this again, I would probably ask people some kind of climate literacy type question, because maybe people who are pulling out those more specific numbers have a bit more knowledge than people who are going just for like a 4 degree or.
Why did you ask it in the free text box rather than on the scale? Because the numbers would be usually distributed, I guess, because of that.
Because of what people type. Yeah, I think it was just to keep it really simple. And to allow, you could have done a scale, but then we didn't want to give people any bounds, right? Because would the scale it'd be weird to give you a scale of 0 to 1,000, because we're kind of saying go high.
How many respondents?
So 196. And I guess one thing that we weren't able to do in the design of the experiments I've shown you was to ask people this question before or after they did the things that we're interested in. If you do it before you've primed them, if you do it after, their responses are diluted by all the numbers you've given them. So this was kind of our shot at getting a bit more information, but obviously it's not very exact. Okay, so we're then interested in understanding, we've got these three groups, they appear to interpret the information differently. How can we predict who ends up in which of these groups? You know, why might I be so convinced that things are going to be terrible and someone else is convinced that everything's going to be fine? So of the 1,000 people that I've shown you, 400 of those, we collected some additional information from them. And we're going to use that to predict which of the groups they fall into. So we collected some general demographic information, so age and political belief. Yeah. Now we've done, can you tell me what it says? Because we've lost the chat thing.
I wonder how much people's best guess is influenced by constantly hearing temperatures associated with targets rather than projections.
Yes, I think that's a really interesting point, and something that will kind of come onto a bit, but the idea of how your prior beliefs are shaped about the future, and whether the people endorsing the current trajectory is because they think it will be that, or just because that's what we hear the most about. Okay, so we had age and political beliefs, and then we had some specific questions related to climate change. So the first thing we wanted to know was whether people had personal experience with climate change. And we included this because personal experience with climate change has been shown to have links to people's risk perception of climate change. We included climate anxiety questionnaire, which measures people's distress in response to dangerous changes in the climate system. And we also included a behavioural willingness scale. So this includes, it has 3 subscales. So it's people's willingness to engage in societal actions. So maybe like paying more money for green energy. People's personal willingness to take action. So that does include like smaller scale things like I'm willing to turn off the lights more often or to take public transport. And also an advocacy index, so the extent to which you would support particular political candidates or encourage your family and friends to support those candidates. And I just want to note that in this sample of 400 people, our spread of the group membership was slightly different. So we still had the majority group being the maintainers. We had 30% of people were pessimistic and 10% were optimistic. And obviously this could just be random sampling, but I think what's more likely is this was the last experiment that we ran. It was run in February 2023. The other experiments were run in, I think, November 2022. And I think in that timing, the discourse had probably shifted away from that best case scenario being as achievable as it had been when we first ran those experiments. So it was quite soon after one of, I'd lose track of the COP numbers. Would it have been COP 27? Well, I'm good. If no one knows, that's good. Okay, so what I'm now going to show you are the results. So we ran a regression analysis using these, so age, political belief, personal experience, climate anxiety, and behavioural willingness. We used those to predict group membership. So what this shows is the probability that you fall into one of the groups. So for personal experience, the top 2 bars, so this dark blue, is the probability that somebody is a maintainer. Then the pale green colour is the probability that they're a pessimist, and the light blue is the probability that they're an optimist. But these probabilities are split by how you responded to personal experience. And the result to note here is that for the pessimists, so the greeny colour in the middle, there's a significant difference between the personal experience. So people who did have personal experience with climate change were more likely to be in the pessimist group. The personal experience didn't affect the optimism and the maintainers. So we then have a similar graph here for age. And again, what you can see is you've got the the maintainers at the top, so the probability for being a maintainer is generally higher across all of these graphs because most people are maintainers. Now, the pessimists, it looks like that as age increases, the likelihood that you're a pessimist decreases. That result's not significant, but the effect on optimists is significant. So the older you are, the more likely you are to be an optimist. Now, for behavioural willingness, I'm just going to focus again on the optimists because this is the only significant effect. The lower your behavioural willingness, the more likely you are to be an optimist. So we've got older people with a lower willingness to take climate-related actions. And then finally, for climate anxiety, again, it's the optimists where we see a significant predictive effect. People who were more anxious were more likely to be an optimist. So this group of people are less willing to take action, more anxious and older. And I think that's not what I would have predicted prior to running this. So if we'll come back to that in a minute, and if anyone's got any thoughts around that, I'd be really interested to hear what people think. And then finally, just for completeness, the politics graph, but there were no significant effects there. So none of those differences came out. In subsequent studies, rather than looking at people's political party affiliation, we've used a scale. So we say people sometimes talk about politics as being on the left or on the right. If you have a scale of 0 to 10, where would you situate yourself? And that is a bit easier to interpret rather than having to classify people into these groups. So a quick summary. So the pessimists, the only kind of predictive variable there was personal experience, made you more likely to be pessimistic about the future. And for the optimists, we saw older people with a lower willingness to take action and a higher level of climate anxiety. Okay, so now let's take a look at the climate scientists. So this will hopefully answer some of your questions. 80% of the climate scientists we asked endorsed the current trajectory. So they are the maintainers. 2%, which was 2 people, endorsed the best case scenario, and 18% endorsed the worst case scenario. And now if we place the results from the climate scientists next to the general public, I have plotted the optimists down here, but I'm not going to talk about them because it is just 2 people. So if we focus on these 2 groups, and I think this does answer the question from earlier, the majority of climate scientists, you see here that it was split between normal and uniform as the kind of main response categories. Here, the main response category for 80% of people is that these values are normally distributed. But you are still seeing this effect of skewness within this sample. So even in these people who believe in the current trajectory and perhaps have some understanding of how these models are generated, for the best and the current scenario, there are people endorsing those hotter temperatures, and for the worst case scenario, they're endorsing the cooler temperatures. Now, the climate scientists who were pessimists didn't quite follow that pattern of endorsing the normal distribution, and I'm going to show you a bit of data about who these climate scientists are, and that might answer these differences in distribution responses, because the pessimists are doing exactly the same as the general public, but to a greater extent, and they're endorsing the hotter temperatures across all 3 scenarios, slightly less in the worst case scenario. So the climate scientists were recruited from mailing lists associated with the ICRR and several mailing lists at Bath in the UK. And so I'm going to show you a bit about the makeup of our climate scientists. So if you look up here at the graph here that says country, I've split the responses in terms of whether people were optimists. Again, it's 2 people, so we're not really going to pay attention to that, but whether they're maintainers and pessimists. So green is Australia, and this orangey colour is the UK. So in the pessimists group, everyone's from the UK. So then we might say, oh, well, that's just, if you're in the UK, you're really worried about climate change. I'm not sure that that's necessarily what's going on. If we then look at research area, you'll see that the pale blue are physical climate scientists and the darker blue are behavioural climate scientists. So now we start to see that the pessimists are predominantly behavioural climate scientists. So maybe they just know less. They're less numerically literate, or they have a better understanding of how these models are generated. But the issue here is those are just my hypotheses because the sample size there isn't enough to use these as predictive factors for group membership. We had also had years in research and age, which are highly correlated, but we're not seeing any kind of particular differences. Politics is, as you would expect, everybody's from the centre to the left in the sample. Now, we ran that same analysis that I showed you, looking at what predicts people's group membership. But as I said, we've got this small sample size. And so we don't see, I mean, it might be that there are no effects, but I'm assuming it's also due to the small sample size. But because I am aware that people here might have taken part in the study, I just wanted to show quickly the plots for the levels. So we had the climate anxiety, the behavioural willingness and the risk perception. Again, optimists is only 2 people, so we can't really say much about that. There don't appear to be any kind of major differences between these groups. Potentially some differences in personal experience with climate change. So this would, if this was an effect, it would be opposite to the general public. So the pessimists were had less experience of climate change than the maintainers. But again, we would need a much bigger group of climate scientists, which I don't think we'd ever get, but maybe we can hope. Okay, so to summarize these results, we see that, so as I said at the beginning, everyone who took part in this study said that they believed in climate change. Now, it wasn't anthropogenic climate change that we are, no. Yeah, I always say anthropomorphic, and then I'm like, no, I did say the right thing. So everyone believed in climate change. So even in a sample of people who acknowledge that climate change is happening, their optimism and pessimism levels about our ability to achieve emissions cuts is influencing how they interpret these identical numerical ranges. And this complements findings that have shown that your beliefs about climate change influence your interpretation of statements of uncertainty. And here we've shown that with statements of uncertainty mapping onto distribution perception. And again, that's broadly consistent with this idea of motivated cognition. And certainly for the optimists, we found effects of age, behavioural willingness and climate anxiety, and for the pessimists, personal experience. I think the optimism group is interesting. So we named them optimists because they were endorsing the best case scenario. So that kind of seemed logical. But those predictors leave a slightly more confusing picture of whether these optimists are hopeful about the future, they had slightly high levels of anxiety, or whether it's more apathy, the lower willingness to take action. So I think that's something we need to think a little bit more about. So when I gave this talk 10 months ago in Bath at the Institute, I had some what next steps, and I can now report that some of our what next steps are actually happening. So one of the things that is interesting here is that we're asking people to engage with these future scenarios, but it appears that people are heavily rooted in what they already believe. So they're not fully engaging with what we're asking them to. And so one of the ways to kind of potentially influence this is to use narratives or storytelling to enrich the scenarios and to get people to kind of step into this future world. And I do think that's important because when you give people projections, they need to be meaningfully interpreted that this version of the future could occur. If it does, what do you think will happen? Ben's honours student, Ellen, is currently running a study similar to what we've shown, but rather than giving these very light, the current trajectory is business as usual, really fleshing out what that might look like for people. And I think the other aspect of this is that, do most people endorse the current trajectory simply because this is what we hear about the most? So is it that they really think this is what's going to happen, or is it that when they Google things, this is the most kind of common number that comes up? So there's this idea that we perhaps need to increase the discourse around other scenarios. And actually it was a paper in PNAS about talking more about worst case scenarios that kind of inspired us to run this project. So that's the kind of the overview of our work there, looking at different climate futures. I'm now going to talk a little bit more about distributions and people's understanding of probability distributions. So in climate change communication, we do often, as I said, present people with these ranges as a way to communicate uncertainty. And we do this in something like a weather forecast, but also I've seen recently I can't remember the name of the New South Wales project, what's it called, Ben, about the hot days? NARCLIM. So that's like a public facing website, and it gives a kind of, by 2030, we expect there to be X many number of hot days, as low as something and as high as something else. So it's a really common way to communicate with people. But to some extent in doing this, we're making an assumption that people can either learn or understand the probability distributions. And this is important because it's going to have an influence on how they then respond to this information and the types of actions that they take. Now, this assumption that people learn probability distributions is also reflected in psychology. So a lot of psychology research just assumes that when you encounter various events in the world, you automatically infer what the underlying distribution is. But until recently, this assumption was untested. And then Ben and Abra and I came along and tested it. So I'm going to talk a little bit about our work on that and how it relates back to the kind of climate change communication. So if you have someone who's trying to answer the question, has the climate in my local area really changed, or has there simply been a run of rainy days? One way they might do this is they might learn the frequencies of different weather patterns and then map this onto a probability distribution. Now, the idea of that, if you're not in psychology research, might sound like very unplausible, right? It seems like a very strange thing to do. But this has really become quite deeply ingrained in psychology, and in particular in the kind of the Bayesian influence on learning. So the other way that someone could answer this question is that they could build a representation of various aspects of the environment and use this to answer the question. So I might come along and say, well, I think it used to rain every 3 days and now it's raining every 2 days. And I would then be able to give an answer to that question, but I haven't mapped out the probability of all the likelihood of the rain. Now, people are able to come up with complex judgments and decisions using either of those strategies. So we ran a set of behavioural experiments to really test whether or not people do learn these or automatically learn these underlying probability distributions. So I'll talk you through the general task that we used and then show you some of the results. So it's really, really boring task. You sit in the lab and a lovely, this is us making it fun, right? A red circle drops down from the top of the screen. It's like a computer game. You click on the red circle and a number appears. And you do that 180 times. And then you have seen a probability distribution of numbers. And specifically, what we showed people was a noisy bimodal distribution. So it had 2 modes and then a little bit of noise across the whole range of numbers. So the numbers range from 0 to 100. So that's your learning phase. You've then been exposed to the distribution. And then we have the distribution elicitation phase. So we wanted to keep these similar. We didn't want to ask people explicit questions about distributions. Instead, we said to people, now you've seen that list of numbers, try to recreate a sequence of numbers that's as similar as possible to the sequence that you just saw. And they do this on a slider. So they have the numbers 0 to 100, they choose the number they want, they press the space bar, and they do that 180 times. So then you can look at the difference between what they were exposed to and what they reproduced and see whether they can learn these probability distributions. So here you can see the pink is the underlying distribution I explained. So you've got a lower mode that's a bit fatter and a narrower upper mode. And you can see under the blue there, you've still got that all the numbers between 0 and 100 occurred at least once. And the blue are the data from, there were 50 people in this? I don't know. So this is from the first experiment, we had about 50 people, and that's the kind of average responses that people gave. So I don't think that that's particularly good evidence that people can learn a probability distribution. But we thought, well, everybody is really convinced that they can do this. What conditions might be necessary to get somebody to learn about the probability distribution? So we ran 5 experiments where we increased what we call the mental scaffolding of the environment. So we gave people features or cues in the environment to help them break up these numbers and learn about the frequency of the different numbers. So we did things like, we gave them verbal hints. So we said the numbers fall into 2 groups, or some numbers are more likely to occur than others. We put the numbers in different colours. So we would have the upper mode and the lower mode in a colour and the noise in a different colour. We also gave them rewards. So we said, you know, when you see the numbers in blue, you can earn some more money. So we did all of these things to try to increase learning in the environment. And I'm going to show you the results from where they have all of this. So as much help as we could possibly think of to give them. And when we do that, they're starting to be able to learn what's going on. They've had a lot of help. So they've really got the idea that there's a lower mode and an upper mode, but there seems to also be potentially some evidence that they've put something extra in the middle. And then the other version of increasing the mental scaffolding is to make the signal to noise ratio really, really strong. So if you do that and you give people a discrete probability distribution, i.e. you remove all the noise and you just see the numbers in the 2 modes, then people do seem able to do this. So we don't see evidence that people, I mean, I don't think that's surprising to most people, that people can't just infer immediately what's going on from a series of events that they see. But they can reproduce distributions when we constrain the hypotheses that they're building about the environment. So we, you know, someone might be thinking, okay, blue numbers are occurring more than orange numbers. So when they reproduce the distribution, they start to reproduce more blue numbers, which might be the upper mode. Now, we looked at the individual's responses to, so the data I just showed you was the aggregate across all participants, but when individuals respond and they don't learn the distribution, it's not just randomly that they respond. There seem to be some patterns in what they think has been going on. So this is the idea that they might be developing their own hypotheses about the patterns in these sequences, even if they're not the ones that are truly there. So in that first condition where you don't give them any clues, somebody might think that there are 3 modes, for instance. So what we're planning to do now is to use this type of task as a framework for looking at how people learn climate change related patterns. So for example, if we were to show people these sequences of numbers, but now they are the temperatures from across the year, they're not in a vacuum of context, we give people the context and see how they generate these representations and the types of rules and hypotheses they come up with to learn this underlying structure. And then that also relates back to this idea of, well, how does that link to their prior beliefs about climate change again? So if they're feeling more negative about the future, does that influence their perception of you know, how many hot days there were? Does that influence the types of rules that they generate about their environment? Okay, thank you.
Very much. Any questions from here or online?
General comment. So something I struggle with when thinking about climate change and probabilities about climate change is that you're talking about probabilities of a single future event where you'll never be able to learn whether those probabilities were good estimates. Like for instance, let's say it's 2080 and you see that the degrees of warming was 3 degrees. You don't know if any of the probabilities we're talking about now were good estimates or not, because it's a single event. Like the models that forecast future elections, you'll never learn, even if the party that won that you assign 99% probability to, you'll never learn if that was a good model. So I'm just wondering, like, how are these people, it goes back to this, what's actually correct. But to me, like, there's no correct answer, and everything's just close to guesswork about probabilities.
Yeah, so I think that it's exactly that. There's a real disconnection between perhaps what's being trying to be communicated and what's actually kind of maybe more logical to somebody interpreting the information. So it might be more logical for me to have like a kind of idea of sort of a broader idea of how likely everything is to occur and to respond in line with that, rather than to be sort of in a particular model. Is that kind of what you mean?
I just don't see how a layman could have any meaningful information to answer this question, I guess is what I'm trying to say. And so they might just be guessing based on feeling or something, or which I think was one of your points, actually.
Yeah, so I think it's just the idea then of, is there a benefit of communicating this information to people in this way at all? What's it actually doing? Because it's certainly not engaging the decision maker in the way that the scientist, I use that broadly because it might not be, intend it to. So I'm certainly not saying that we want to get people to be able to do this, but we want to at least build a better connection between what's being intended and how it's being received.
Yeah, gotcha.
Right, I had a question.
Yeah, I was just curious about how the next step is going to work, because the main part of the talk was to show people do have some notion of what the best case, worst case scenario is, and what the distributions of different temperature values within those cases might be. So that's very different to your distribution learner.
Yeah.
So were you going to sort of like present a distribution that may be different to what people currently believe, and see if that?
Yeah, exactly. So I think for this, it's more of like a experience-based paradigm. So whether or not, if you see a kind of sequence of events that's skewed in one direction or another, how does then that influence what you replicate as a function of perhaps your beliefs about what it was going to be like. But I would also just say that in the first half of the talk, we were mapping their responses onto probability distributions. I don't see that as evidence that people learn the underlying distribution, if that makes, and someone said that on the chat, said that Gab's paper is really relevant. And actually Gab was someone that Ben and I spoke to quite a lot about when I was here, I think 2 years ago. I got deep into reading climate modelling papers, which was way beyond me, but Gab was very helpful with that. So. And someone else has asked, did you look at the sequence that people produces? Yeah. So I'm sorry, I'm just reading. Yeah, so we did look at the sequences. I'm looking at Abba to help remind me to jog my memory, and we didn't see any particular effects on
the order in which they reproduce the events.
Yeah, and I think that possibly if that might be because there wasn't really a pattern in the underlying sequence, but I think that idea is really interesting. And the question we did ask people said, if you think that there are any patterns and sequences, do try to reproduce them. So I think if you use a slightly different underlying distribution, that might be something that people were trying to do.
I don't know if it's any relevance at all, but there is the right answer here.
Oh, that is relevant, yeah.
But there are two right answers. That range of whatever, 2 to 4 degrees, is what the climate models tell you the range is.
Yeah.
And we can track back as to where those numbers came from by the Intergovernmental Panel on Climate Change or whatever. So there is a right answer. However, what we don't know is how right that right answer is. So the range could be completely wrong, but we do know where that range comes from, and in principle, the scientists should have been able to make a judgment on that. And I don't think it's normally distributed. It's a range from the climate models. Now that range is almost certainly imperfect, and the stuff that Gab's done on model independence is highly relevant to that. Yeah. But I don't think it's normally distributed. I think it's each of the values in that range is equally probable.
And so, just out of interest, why do you think the physical climate scientists felt that it was? I mean, I know it's only like what 60 people, but
I'm not allowed to say they're wrong, am I?
Well, it was just really interesting because.
So that range comes from a subgroup of the physical climate scientists sitting in rooms analysing information and probably in different ways bringing the climate models together with the independent analysis of climate sensitivity. And that in itself is a complete nightmare. And so there's probably expert judgment going on and how they choose to interpret that range. But the actual range comes from the simulations of the climate models.
Yeah, so so there's been a paper that gave people these ranges and it explained that they come from ensemble model predictions, and it kind of it gave people a picture and it said like there's this model, this model, this model, and to show that it comes from somewhere. But they didn't then ask about a distribution type thing. I think they're more interested in trust. But it's interesting that if the climate scientists are struggling to see that, like that.
But I think to go to Andy's point, I think it's like saying, coming up with some relevant question in psychology and saying, well, we asked a bunch of psychologists.
Yeah.
Psychologists as a group are extremely diverse. Look at various schools that we're in. So there's climate scientists for whom this is what they do, and there's climate scientists for whom this specific kind of question is tangential.
I think that's absolutely right. I mean, the vast majority of climate scientists would have no more understanding of where that range comes from than reading the summary for policymakers.
So that they would be the same as the behavioural scientists in that sense.
Yeah.
But then it's interesting because I think it was, I'm going to throw Gab under the bus here. I think it was Gab that said that they would
Where is Gab? Is he in his office or going crazy?
Be normally distributed. So, I mean,
but that's in the limit with infinite numbers of models that are not.
And the fact is they're not
correlated,
made in that way. So then, yeah.
I think that, going back to the way that you framed it at the start, that the interesting question in here is, how do people use that information and interpret it differently as a function of which future they think we're in?
But I also think it's interesting to the question of, is there, like, the fact that it's impossible to answer whether there's a correct answer, which kind of shows the messiness of the question.
You could answer it for a specific set of numbers from a specific statement in the summary for policymakers, I guess.
I just wanted to ask you, Andy. So this range, So this range, well, it's heavily related. So this range is for a fixed emissions pathway, and the emissions pathways, it's a continuous variable. So it has a probability of virtually zero of actually occurring. How can you infer probabilities from a range that's based purely on a model?
Say that again slightly.
Simple. The range. So let's say the range is for SSP5 7.0. The range is 3 to 4.5 degrees, because that's what you get from running 50 different climate models. SSP3 7.0 or whatever it is for a fixed emissions pathway. So what emissions we generate each year from now until 2100. And that's a continuous variable. Each year it's a continuous variable. So the probability that we're actually going to emit the same pathway of SSP3 7.0 is zero, like literally zero. So when you try to map probabilities on a range like this, it ceases to make sense to me, like in terms of which is likely to happen, because it's conditional on an event that has probability 0 already.
Yeah, I'll take that. How helpful is that statement that you made? Because you've got to tell policymakers what the response would be to this emission pathway, and you saying it's a 0 probability of that emission pathway exactly following that pathway. How is that helpful?
No. For that purpose, I understand entirely why they're doing what they're doing. But what I'm struggling with, I guess, conceptually, is how you can infer a normal or uniform distribution out of these ranges at all. It doesn't make sense to me.
Well, I guess it's because actually what you're inferring is to do with how the model estimates were generated. So it's not, by the time you get to the snippet from the Guardian article, what's being presented to the public is so far away from what was actually intended, which is what you've explained and how it works. So you've there's a complete disconnection between, you're telling the public, oh, we think it's as low as this and as high as that. But actually you're actually just telling them what the models are predicting for a scenario with 0 probability.
Yeah, gotcha. Sorry, I'm not trying to say this isn't interesting or not useful.
No, I don't think you are.
I'm trying to argue that I don't think it's possible for there to be a right answer, for there to be a true probability distribution for this range. You can't take probabilities. Anyway, it's just my thing.
On that point of contention, we'll leave Tim and Andy to nut it out. I would like to thank Alice again for a very engaging talk. Please stick around for lunch and look out for the next seminar, which will be, I'm looking at Alison or Alana, 15th of May.
No, this month.
Oh, 15th of April, even better. We'll send announcements out. Thank you very much.